Okay, so last time we started to scattering. So basically we are considering a scatter whose dimensions, is small relative to the incoming wavelength of the electromagnetic wave. So we are working on at long wavelengths relative to the scatter. So first we will study for only one scatter, and then we will distribute the scatters to the medium and investigate the scattering again. So suppose that incoming wave propagating at n0, and it has the components of the electric field and magnetic field, of course, E incident and H incident. So they are plane waves. So wavelength is greater than the size of the scatter, and after the scattering you will have some sort of spherical waves. So if we denote the incoming wave as E incident as some polarization, so I will denote now as a unit vector, and it's also a complex number, some polarization, amplitude of the field, and phase term. And the incident magnetic field could be written as N0 cross H incident over impedance. So the components of the electric field and magnetic field induced a oscillating electric dipole moment and magnetic dipole moment. So if you have some material which could have the dielectric constant and magnetic permeability, and the components of the electromagnetic wave E and H fields will induce some oscillations, and it will magnetize and polarize the material. So basically you will have some electric dipole moment oscillating the frequency of the incoming wave, and some magnetic dipole moment oscillating with the same frequency of the incoming wave. So we know that if we have a oscillating electric dipole and oscillating magnetic dipole, we have the radiation. And last time we studied that we investigated the scattered fields as a radiating fields of the electric and magnetic dipole fields. So we have shown you that the E scattered field could be written as radiating fields of electric dipoles and magnetic dipoles, basically dipoles. So that goes 1 over 4 pi epsilon 0 k square e to the I k r over r. This part is the spherical wave term, and the rest is n cross p cross n minus n cross m over c. And H field orthogonal to the propagation direction and the scattered field, so that is nothing but n cross E scattered over impedance. So after the scattering, the propagation direction of the wave is some n, and it has E scattered and H scattered. They all mutually orthogonal to each other, and they are spherical waves. So the sources of the scattered waves are the electric dipole and magnetic dipole. Then, so this is the summary of what we have done last time. Then we try to define that the scattering cross section per salt angle so that is area over per salt angle, and the scattering cross section per salt angle depends on incoming direction of the waves, initial polarization, and after the scattering the direction of the propagation and polarization after the scattering. So we have said that this could be defined as power emitted per salt angle of the scattered waves. So scattered waves are distributed through the all salt angles, and incoming waves are the plane waves that has the power per area. So you can define that area element, and through that area you can calculate that the power per area. So that is nothing but P incident per the area. So if you look at the units, this is the power per salt angle, this is power per area, so power terms cancel out, and you can get as a unit as a area per salt angle, and this is the area per salt angle. If you want to calculate that the total scattering cross section, that will be the integral of the scattering cross section per salt angle through the all salt angles, and the units will be the area. So basically we can write the power per salt angle of the scattered waves as 1/2 real part of r square n dot E scattered cross H scattered divided by 1/2 real part of an incident propagation direction of the incident wave and the field incident electric field cross H incident. So I think we have a complex conjugate here. So let us define that the incident electric field by including the polarization more carefully. So let us say that the E incident is in that form, and let us say that the polarization in that form. So E0 complex number, in general the polarization could be expressed in terms of complex numbers as we did for the circular polarizations in the beginning of the course. That E incident and let's say along epsilon 0. So if you pick up this definition and plug there, which we did last time, you are going to obtain the following. So, for example, for that term, you will have N0 dot E incident cross H incident complex conjugate, and this will be N0 dot E incident, which I defined here, epsilon 0 complex conjugate dot E incident along epsilon 0. So last time I defined as a different unit vector x hat, if you look at your notes, but we can define this. This is more proper, defining that the direction of the polarization as epsilon 0. So we have N0 here, dot product E incident, that cross product H complex conjugate, that is nothing but N0 cross E incident initial polarization along E incident divided by Z0 along E0. So what I did here, we have E incident, which is equal to projection of the E incident along the polarization, and it is along a unit complex vector epsilon 0. So N0 dot E incident is this term, and this whole term is H incident complex conjugate. So if I take the complex conjugate, I should take the complex conjugate of this and that one. This is a real unit vector. So what we did last time, so we have double cross product here. So first term will be A dot C, first term, and the last term of the scalar product along N0. So you will obtain epsilon 0 complex conjugate E incident times epsilon 0 complex conjugate E incident complex conjugate divided by impedance of the free space, and epsilon 0. So this is along what? Epsilon 0 complex conjugate, epsilon 0 dot epsilon 0 complex conjugate along N0. So this is 1, and if you take the scalar product N0 here, so put it this here, so that will be 1, and N0 that will be N0 will be 1 again, and you will obtain epsilon 0 complex conjugate E incident absolute square divided by impedance. And if you look at the other term here, this is, if you call this is A, B, and C, that is nothing but A dot C along B. And if you look at that, the A dot B, so the other term will be what? You have something there, but you have epsilon 0 dot N0. What is the epsilon 0 dot N0? 0, because this is the polarization of the incident wave. This is the propagation direction of the incident wave. Polarization and propagation are orthogonal to each other, and this term will be the 0. So If you do the same thing for the scattered waves, you will get the same structure. Therefore, scattering cross-section per solid angle will have the following form. So from above term, you have 1/2 r square and epsilon, the polarization after the scattering, and that product with the scattered wave. If you do the same work for the above term, you will get the same structure exactly, and that will give you the following. Epsilon complex conjugate dot scattered field divided by 1/2 epsilon 0 complex conjugate dot E incident square, and that should be divided by impedance. So they all cancel. So as you see that the scattering cross-section per solid angle is related with the scattered field, that product with the polarization after the scattering. So basically this whole bunch here is nothing but the following. So if you take the epsilon 0 and that product with the E incident, you will have unity here, and if you take the absolute square of this will be unity again, and you will have E0. So this term will be nothing but E0 square, amplitude of the electric field of the incident wave. Now let us plug or substitute the scattered field to this definition and estimate that the scattering cross-section per solid angle. So what we need to calculate, basically, we have to calculate that the polarization after the scattering, that product with the scattered field. So let us do this calculation and estimate that evaluate that the scattering cross-section per solid angle. So I don't need about term. So we are going to estimate that term. So basically, if you take the absolute square of this and multiply by r square, that r square over r square will be cancelled, and you will get the following. You have 1/E0 square from here, and if you look at that, the epsilon complex conjugate that is scattered absolute square, you will have k to the 4 over square of 4 pi epsilon 0 and 1/r square, but that r square will cancel with the other r square. So as we thought earlier, so the power and the scattering cross-section does not depend on any distance because they are spherical waves. And we have to calculate this epsilon complex conjugate dot with E scattered field, and that is nothing but n cross p cross n minus epsilon complex conjugate n cross m over c, and then take the absolute square. And also you have that term, the absolute value of the e to the ikr is 1. So maybe I make a mistake here. When you take that the dot product with the epsilon complex conjugate, you have one this term, one of them that term, and the other one that will be this term. So basically this is the situation. So epsilon unit vector dot product first n cross p cross n, then epsilon complex conjugate dot with n cross n. So the above term could be written in the following form: epsilon complex conjugate dot. So what is this? Double cross product, and this double cross product is nothing but n dot n along p minus n dot p along n. So which term will be the 0 here? N dot n is 1, and epsilon complex conjugate dot p is something. But if you look at that this scalar product, epsilon complex conjugate dot n, what is this? This is the polarization after the scattering, and this is the propagation after the scattering. And if you look at here, n and the polarization after the scattering will be mutually orthogonal to each other, so that will be 0. So basically the scattering cross section per salt angle will be k to the 4 over 4 pi epsilon 0 E 0 square epsilon complex conjugate dot p minus this term, but you can arrange this term as a n cross epsilon complex conjugate dot m. So that term takes the positive, so this is nothing but, this term is nothing but n cross epsilon complex conjugate dot m with the positive sign. So you will get n cross epsilon complex conjugate dot m over c absolute square. So this formula represents the scattering cross section per salt angle, and the sources of the scattering cross section per salt angle is the electric dipole moment and magnetic dipole moment. And here, in all sorts of formulas related with the dipoles, these are the dipoles, are related with the k to the 4. K to the 4 is nothing but omega to the 4, related with the omega to the 4, and that is related with what? 1 over inverse of wavelength. So basically this term is important in the Rayleigh scattering because that tells you that higher frequencies are scattered more and the lower frequencies are scattered less. And omega to the 4 is related with the 1 over lambda to the 4. Lambda is the wavelength. If we compare with the red light and green and whatever violet, which one scattered more? Which one has the more wavelength, longer wavelength? Red. Red has the more longer wavelength, less frequency, therefore it scatters more. So that is the explanation of the that will be the explanation of the blue, why the sky is blue. We will come to this later on again. So that is related with the Rayleigh light scattering. Basically, we are working on what wavelengths much greater than the size of the scatter, and we are finding that the scattering cross-section per solid angle related with the omega to the 4. That means that the higher frequency is scattered more. So first blue light explanation was taught by the Leonardo da Vinci at 15th century, and he suggests that the sky is blue because sun is white, at dark the night is dark, so mixture of the a little dark and the white make blue. So he was first taught, and then it was waited 350 years roughly. Rayleigh suggests that the sky is blue because the electromagnetic waves scattered from the atoms of the atmosphere. But I have to tell you one thing here. This is related with the omega to the 4. Since we have dipoles, if we have quadrupoles, so if the dominant term of the quadrupoles of the atoms or molecules, whatever, this goes with the omega to the 6. It's with the 6th power. So instead of here, if we have quadrupoles, that goes with the omega to the 6. And if you look at that, we calculate that the quadrupole radiation of the quadrupole, we see that the H field is proportional to K cube, if you look at, and therefore H square is proportional to the K to the 6. K to the 6 means omega to the 6. So if it were the quadrupole terms are dominated, this will go with the omega to the 6th power. Now let us do examples. We have the formula for the scattering cross-section per solid angle, and let us study the scattering cross-section per solid angle for dielectric sphere. Then we can work on the scattering from the perfect conductor. So first let us study that the scattering by a small dielectric sphere. Small dielectric sphere. So what I am going to do, I will erase this part. In order to make a dielectric sphere, I will define a dielectric constant, some epsilon. So vacuum has the dielectric constant epsilon 0, and say that the radius of the sphere is A, wavelength is lambda is much greater than the size of the scatter. So if you have a small dielectric sphere, so let's say scattering by a small dielectric sphere. So you have some material with dielectric constant epsilon, that it's a sphere, and electromagnetic waves scattered from that. What will happen? The electric field component of the electromagnetic wave will what? Polarize the sphere. Magnetic field component of the electromagnetic wave does not magnetize because the sphere has only dielectric constant. So in all, mu0 is the same. So magnetic permeability is not different. So basically you will have only polarization P. And that polarization will oscillate with the frequency of the incoming wave. And the magnetic dipole moment will be the 0. basically automatically you will put 0 for the magnetic dipole moment, and you have to know that the electric dipole moment. So how you can calculate that the electric dipole moment? How you can calculate that the electric dipole moment? If you remember from the lecture notes from the first part from chapter 4, you studied that the dielectric sphere with external electric field. You solve this problem using the boundary conditions and the Laplace problem. And the polarization you obtained was the following. P was equal to 4 pi epsilon 0 epsilon minus 1 epsilon plus 2 E cube E incident. So this is a separate problem. You can look at your lecture notes. So basically, if you put the dielectric sphere to the external field, it will polarize. So basically, one part has the negative charges, the other part has more positive charges, and you can calculate that the surface polarized charge density, and you can calculate that the polarization. And you can calculate that the electric dipole moment. So actually, this is the electric dipole moment. Dipole moment. So this was the result when you do that study. Basically, in here, we don't have a static electric field, we have an oscillating electric field. But basically, what will happen, if the field is oscillating at frequency omega, your induced electric dipoles will oscillate. And that is nothing but, this term is nothing but with the same electric dipole moment, but the difference, it will oscillate. So that will be 4 pi epsilon 0. Epsilon 0 is the permittivity of the free space. Epsilon minus 1, epsilon plus 2, A cube, E incident. And E incident is nothing but E incident. E incident here, initial polarization, amplitude of the oscillation, e to the I, k, and 0 dot x, oscillating with frequency omega. So this will be the electric dipole moment of the sphere. So if you put this information to here and take the m equal to 0, you will obtain the following. The scattering cross section per salt angle will be k to the 4 divided by 4 pi epsilon 0 E0 square epsilon polarization after the scattering, that product, this whole P. Square. So let us go one more. Let us write one more time. If you plug the electric dipole moment over there, of course, we will put the space part of this because the time part is already taken into account in the calculation of the power emitted per salt angle, scattered power per salt angle. So you will have 4 pi epsilon 0 square, and the square of this term, that should be a to the 6, and you have E0 square that will be cancelled with that one. And the important thing, the incident polarization of the wave, dot product with the polarization after the scattering, and your result will be the following: k to the 4 pi epsilon 0 E0 square, and 4 pi E0 epsilon 0 E0 square. This whole term will be cancelled, and epsilon minus 1 epsilon plus 2 square, and the square of this a cubed, that is a to the 6 power, and the leftover term, and that is important, we will do some process with that term, epsilon complex conjugate, the polarization after the scattering, that product with the polarization before the scattering. So the bottom line, for an application of the scattering from a dielectric sphere, we will find a simple formula. Scattering cross-section per salt angle will be k to the 4, a to the 6, epsilon minus 1, epsilon plus 2 square, polarization after the scattering, that product with the polarization before the scattering. So this will be the formula. As you see that this is related with that scalar product, and let us try to estimate that scalar product, which is polarization before the scattering and after the scattering. Now let us draw a geometry. So let's say that x, y, and z. Let us take that the incident wave is along z-axis and 0. Therefore, the polarization vectors will be what? Before the scattering, that should be epsilon 0, 1, and epsilon 0, 2. 1 represents the x-axis, 2 represents the y-axis. This is the incident wave before the scattering. Maybe I should put the epsilon 0, 1 to here. So the total polarization of the incident wave could be written as E0 as 1 over square root of 2 epsilon 0, 1 epsilon 0, 2. So you can define this in that form. Actually, this wave is unpolarized because any wave propagates along the n0, and the field, electric field, could be anything along the xy direction. It is not systematic. If it were a circularly polarized wave, then your electric field should be something like this, E incident. Should be on that plane, then you can define that the incident wave as a what? 1 over square root of 2 epsilon 0, 1 plus a complex number epsilon 0, 2. This is circular polarization. That means that the propagation along the z direction, but your electric vector is rotating on xy plane as a circularly. But if you don't put anything here, this means that random. So at any time, your electric field will be anywhere on the xy plane. That means that with respect to the observer along the z-axis, this is an unpolarized wave. So let us take this as an unpolarized wave. If you want to study a linear polarized, that is the simplest case, you can take one of them. This is linear polarized. And this is also linear polarized. One of them is along x, the other is along y. But this is the mixture of this, that means the incoming wave is unpolarized. Unpolarized. After the scattering, let us say that the propagation is n-hat direction, makes an angle theta with the z-axis, and you choose your n vector after the scattering on where? XZ plane. XZ plane. Suppose that scattering takes place along XZ plane, yes, XZ plane. So what will be the polarization vectors after the scattering? So this is n0, this is y, this is x. So after the scattering, if you rotate this vector by theta, which vector will be affected? This will be, polarization of this will be what? Along the x will be moved down on the xz plane by amount of theta. So let us call this is a epsilon 1, makes a theta, and again this is along xz plane. But perpendicular to this one doesn't affect it. So after the scattering, epsilon 2, 0 is equal to epsilon 2. Because if you rotate this vector by amount theta along xz direction, what will happen? Epsilon 1 will shift it down by amount of theta, but the perpendicular to component does not affect it, okay? Now, let us do the following. Let us decompose the scattering cross-section per salt angle into two pieces. One of them is scattering cross-section per salt angle parallel to the scattering plane. The other is perpendicular to the scattering plane. So let us look at the problem in two pieces. Where is the scattering plane? XZ plane. If you look at the XZ plane, how will be the epsilon complex conjugate dot epsilon 0? Parallel to the scattering plane. Parallel to the scattering plane. What is the epsilon 0 parallel to the scattering plane? Epsilon 0, 1 along x direction. After the scattering, it shifted by amount of theta, that is epsilon 1. If you look at the dot product of this epsilon 0, 1 and epsilon 1, that will be cosine theta. So for the scattering cross section, parallel to the scattering plane will be k to the 4, a to the 6, epsilon minus 1, epsilon plus 2 square, and this should be what? Cosine square theta. So is it enough? So not really, because if you define that the total vector in this form, and after the scattering you can define epsilon 1 and epsilon 2. Basically, from this dot product, you will have 1 over 2 factor. Okay? So you can say this is a weight factor, or that represents the nature of the unpolarized wave. Okay? We have 1 over weight of this type of scattering. So that is parallel to the scattering surface. If you look at that, the perpendicular to the scattering surface, before the scattering and after the scattering, they are parallel. Okay? Polarization perpendicular to the scattering surface doesn't change. They are but along y direction. So before the scattering, that was epsilon 0 along y. After the scattering, that is epsilon again along y. So the scalar product will be 1. So basically that will be k to the 4, a to the 6, epsilon minus 1, epsilon plus 2 square 1. So from the weight factor or normalization of the unit vector, unit polarization vector, you will have 1 over 2 here. So basically, if you sum up those things, scattering cross section per solid angle will be the sum of these two. Scattering cross section parallel to the surface, scattering cross section per solid angle parallel to the surface, plus perpendicular to the surface will give you k to the 4, a to the 6 over 2, epsilon minus 1, epsilon plus 1 square, 1 plus cosine square theta. And if you integrate this through the all solid angles, you can calculate that the total scattering cross section, and this whole integral, cosine square integral, will be 8 pi over 3, I guess. And if you calculate this through the all solid angle, you will get the result of 8 pi over 3. Actually, that should be 4 pi over 3. 8 pi over 3, k to the 4, a to the 6, epsilon minus 1 divided by epsilon plus 2 square. So this is the total scattering cross section. So if you do this exercise by yourself for linearly polarized waves or circularly polarized waves or elliptic polarized waves, total result doesn't affect it. Total scattering cross section will be the same. For simple, try for linearly polarized wave. That is the simplest one. So why we are dealing with that the scattering cross section perpendicular to the surface, scattering surface, and parallel to the scattering surface. Using this, we can define that the polarization after the scattering. So there is a new definition, theta pi theta. This is the degree of the polarization so polarization, let us say that polarization of the scattered radiation that is defined as difference of the perpendicular and parallel scattering cross section per solid angle. This is a general definition divided by total scattering cross section. So this is a general definition. So that tells you that take the scattering cross section perpendicular to the surface and subtract with the parallel one, divide to the total one, and you will get some information about the polarization after the scattering. So if you do this for these two pieces, what you are going to obtain? Perpendicular minus this one will be in the parentheses of 1 minus cosine square. This is sine square. And if you divide that the sum, that will be 1 plus cosine square, and your result will be sine square theta divided by 1 plus cosine square theta, because the coefficients are the same. Now, what does it tell us? What does it tell us? These formulas. At 90 degree, if there is a 90 degree scattering, if there is an unpolarized wave, and if it is scattered by 90 degrees, so suppose that the wave is propagating towards to you, which is unpolarized. If it's scattered 90 degrees, you will see that the projection of this, and that will be what? 100% polarized. So is it true? Yes, because when the angle is 0, the polarization is 0, unpolarized. When the angle is 90 degrees, if you look at here, you will get what? 1. So sine 45 square and the cosine, so if you take this, that will be 1. So if you plot this information, what you are going to obtain? So one of them, you can plot the degree of polarization as a function of angle. So what is the angle? When angle is 0 for the forward scattering, when angle is 0, cosine theta is 1. When angle is 180 for the backward reflection or scattering, the angle is 180, cosine 180 is minus 1. So basically, this, let us plot this in this way. This is 1, this is minus 1, and this is 0, and let us say this is cosine theta, goes in this way. So for the polarization, when the angle is 0 for forward, and for the angle is 180 degree for the backward, the polarization is 0. And the polarization is maximum that is equal to 1 at 90 degree scattering. So let's say that this is 1 and this is 0. Okay? So if the wave is scattered by 90 degrees, you will see that 100% polarization. For forward and backward scattering, again you will not see any polarization, and when the angle is between them, you will see some polarization. Let us look at that the scattering cross-section per salt angle. Let us plot that the scattering cross-section per salt angle. So let's say that this axis is vertical, is scattering cross-section per salt angle. And what you see for that case, look at concentrate of this formula. What is the form of this function? That goes 1 plus cosine square theta. When the angle is 0, what is this? 1. When the angle is 180 degree for the backward scattering, that is minus 1, but square is 1. When the angle is 90 degrees, that is 0. So basically, if you plot the scattering cross-section per salt angle, you will have the following structure. The scattering will be symmetric along 90 degrees. So this is for backward and this is for forward. For forward and backward scattering intensities will be the same amount. That will be minimum at 90 degrees, but along above or below the 90 degrees, the function is symmetric. So the same amount of scattering is some angle here and the some angle here. If you take the same angle relative to the 90 degrees, you will get that the same number of the intensity will be the same. So that will be even along the angle 90 degrees. So basically the situation is the following. If you put the scatter here, if you submit a long wavelength here, this is a dielectric sphere. If you put the detectors here, and this is 90 degrees, let's say you put a detector here, some theta here, and if you put the same, if you take this angle, let's say theta prime, and if you look at the intensity with the same angle theta prime, you will find that the same intensity. Okay, the forward and backward scatterings are even. Okay, so the intensity here at theta prime relative to the 90 degrees and the intensity here with theta prime relative to the 90 degrees will be the same. So this is an even function along 90 degrees. So backward and forward scatterings will be the same amount, but for any angle that will be symmetric. So what we learn here, if we send the electromagnetic waves a single scatter, if the wave is initially unpolarized, we can see polarization. The polarization depends on the angle, and the maximum polarization occurs at 90 degrees of scattering. If you look at that, the distribution of the scattering cross-section per solid angle, backward and forward scatterings as an amount will be the same. That will be minimum at 90 degrees, but any offset angle relative to the 90 degrees, you will measure the same amount of the scattering. So let us give a 10 minutes break, then we will take the different examples. Scattering from the perfect conductor we will study.